All right, so let's look at example 5. Now in example 5, if you notice it, you can easily spot the discontinuity. So you can see there's a 2 and a 5, they're numbers. You don't see infinity appearing. Then look at it closely. If I put 2 in this root here, I end up with 1 divided by 0, which is undefined. It means it's a discontinuity at the lower bound. So that's how you test. So from this class going forward, whenever you see an integral, substitute the bounds and see if you're going to have a problem, or you can spot a number in between the bounds that's going to give you a problem. All right, that is not part of the domain of the function that you're trying to integrate. Then you know you have a discontinuity. All right, so in this case, because I see that 2 is going to give me a problem, because the domain of this function is such that x cannot be equal to 2, obviously. So I'll introduce limit. Very important, limit, guys. If I don't see limit, you're going to lose mark. All right. Introduce limit, obviously replace the 2 with the t, since you've already introduced the limit. And tell me what the sign is. We know why it's plus, because we say from the lower bound, that's the direction you're heading to, you're going up, and from upper bound, you're going down. All right. To integrate this, it's easy, it's just a u substitution. So let u to be x minus 2, du is dx, and do change of bounds as usual. All right, do your change of bounds. Most of the other question, there was no need for u substitution. That's why we didn't do change of bound. But once you want to change a variable from x to u, you must do change of bound. All right. Now, if you do that, you end up with new bound that is from t minus 2 all the way to 3. And if you integrate, you end up with 2 root of u. Substitute upper bound minus lower bound, you end up with something like this. When t tends to 2 from the positive side, if you put it in this root, notice you get 0. Right? If you put 2 in there, square root of 2 minus 2 is 0. You just end up with 2 root of 3. There we go. So it's convergent. All right. Convergent. Something I need to mention is some of you guys mostly forget to do change of bound. All right. If you forget to do change of bound, there's another trick. So this same statement that you see here, there are 2 ways of writing it. So I can write it like that to indicate I've done change of bound. Or if you forgot to do change of bound, you can come here and you say that in this case, remember that your x as a lower bound was just equals to t. All right. And your x as the upper bound was equals to 5. All right. When you write it this way, even though I see du over some root of u, but the fact that you've shown explicitly that, look, the bound is actually in terms of x, but I'm integrating in terms of u, you're still going to get your mark. All right. But remember that after integrating now, you need to change u back to x using the substitution that you made. But if you write the bound in this form, you still get your full mark. All right. But why go through all this hustle? Just do change of bound to make your life easy. All right. Someone say explain why u is t minus 2. Let's see. Our substitution is let u be x minus 2. The lower bound is x equals to t. When x is t, if I put t here, what do I get? I get u is t minus 2. And when x is 5, if you put 5 in this u substitution, you get 3. That's the reason why we move from t minus 2 all the way to 3. It's just change of bounds using this u substitution. All right. Hope you're happy now. Let's move on. Example 6. Determine whether this integral converges or diverges. All right. The first thing you observe is you have a sec function. What did I say you're going to do from this point up to the end of your life, the rest of your life? Whenever you see any integral, you need to test the bound. So I put 0 in this function. Sec of 0 is It's fine. It's 1. It's just sec is 1 over cos, and cos of 0 is 1. 1 over 1 is 1. You what? If I put pi over 2, sec of pi over 2 is undefined. Why? Because 1 over cos of pi over 2 is just 1 over 0, which is undefined. You see, there's a discontinuity there. All right. So once you spot that, what do I need to see? I need to see limits to show there's an improper integral type 2. And the sign here is minus. I don't need to explain why. Everyone knows why. Because the upper bound, that's the direction you're heading to. All right. So your x is less than or equals to pi over 2 by definition. All right. So it means it has to be going down. All right. That's why it's a minus. What's the integral of sec? It says ln, absolute value of sec times tan. Like I said, don't show me this step, all right? Because this integral is not an easy integral to move from there to there. But I gave you as a formula that you just need to remember and state, all right? So just remember that integral of sec is ln, absolute value, sec plus tan. Obviously, your bound is 0 to t. There's no need to do change of bound because there's no use substitution here. Now, if you put t there, you have ln absolute value sec t plus tan t minus lower bound, which is 0. Remember that tan of 0 is 0 and sec of 0 is 1. We know that ln of 1 is 0. So this whole piece there just falls off, all right? And you're left with something like this. Now we're looking at the limit as t tends to power over 2. Again, you see there's a problem because tan tends to infinity and sec also tends to infinity when t tends to power over 2. What is tan of 90? Tan of 90 is sine 90 over cos of 90. Sine of 90 is 1, but cos of 90 is 0. 1 over 0, you see where the problem is. It's undefined. Similarly to sec is 1 over cos. We know that cos of 90, again, is 0. Therefore, 1 over 0 is undefined. Your conclusion is that is divergent, right? Because you end up with ln of infinity plus infinity, which is just infinity, and it's divergent, undefined. All right. Any question? So I say when writing the exam, if we are going to write on campus, we will have any formula sheet. Nice try. The answer is no. At UJ, we don't give formula sheet for mathematics. If you notice it, you don't need a formula sheet, right? You just need to know the few formulas I need to remember. And if you forget something, you go back from first principle. All right. Let's look at example 7. They say evaluate this if possible. Nice one. I like this kind of question. Evaluate this if possible. Now, let's see what happens. What did I say you're going to do whenever I see an integral now that you're very good integration? Is that you're going to test the bound, right? So I'm going to put 0 in there. 0, I get 1 over 0 minus 1. Oh, it works. It's minus 1. I put 3. If I put 3, they have 1 over 3 minus 1 is 2, so it's half. It works. So, but don't be quick to say that because both bounds is fine. The lower bound, the upper bound, this part of the domain, then I'm done. I can just integrate. You must check. You see that x cannot be equals to 1. You check here. So if x is 1, what do I get? The function is undefined. So if you check the domain of this function, x cannot be equals to 1. But 1 falls in between this interval. All right. 1 falls in between that interval. So in summary, for this integral to be convergent over an interval, it has to be convergent over at every single number in that interval, right? So if I give you integral from a all the way to b of some function f, all right, dx or dt, or depending on what the variable is, for this integral to be convergent, all right, it means that in between this interval, if I choose any number in between this interval, it will be part of the domain of f, all right? So it means f is continuous across all numbers, including the endpoints as well. But in this case, notice it's from 0 to 3. Just play this again. So from 0 to 3, there's a 1. Do you agree? So if I say from 0 all the way to 3, it means I need to test 1, I need to test 2 as well. All right? Or even not 0.1, not so there's so many possibilities. But quickly you can spot from the domain of the function that x cannot be equals to 1. But the fact that 1 lies in between that interval, it means that there is a problem at 1. And how do we solve this? We say you split the interval into 2. So it's going to be from 0 to that number that causes a problem, which is 1, plus the integral from that number that causes the problem all the way to the upper bound, which is 3. See, now you have 2 integrals. All right. Now, when dealing with this kind of question, my advice is instead of solving both of them simultaneously, just if you can simplify one of them and show that it's divergent, you can conclude that the whole thing is divergent. You don't need to show this other integral. All right. If you do this one alone and the conclusion is that it's divergent, then there's no need to do this other one. All right. The only catch is if you do this one piece and this integral is convergent, then you have to see what happens with this other one. All right. In this case, I choose to do both of them simultaneously because obviously I have enough space and ink to write. So we know that there is a problem at 1, and the 1 is on the upper bound. That's why I say limit as t tends to 1 from the negative side. We know again there's a problem at 1 here, but now it's a lower bound, so it becomes limit as t tends to 1 from the positive side. It's an easy function. It's just ln absolute value x minus 1. Then absolute value x minus 1. Plug in the bounds, so upper bound minus lower bound. And it simplifies to something like this. Now let's see what happens. When t tends to 1, if you put 1 in here, you have ln of 1 minus 1 is 0. All right. You see that it's undefined. All right. So I've already showed you guys the sketch of ln is. I'm going to do it again because some of you weren't listening when I was doing it. So it looks like this. And it cuts at 1. There we go. Now, what happens when t approaches 1 from the left? So if you are approaching 1 from the left, you notice that this whole thing here is going to end up in ln of 0. All right. And if you try this other side, when you approach 1 from the right, so 2 over 1 minus 1, it's just 2 over 0. Again, it's ln of infinity, which is just infinity. All right. So be careful, we have minus infinity plus infinity. Again, you don't have a number, there's no definite answer, there's no such thing as minus infinity plus infinity equals to something. The conclusion is that it's divergent. All right. Very important, that's why I ask you if it is possible. Evaluate this if it's possible. All right. Even if I don't say if it's possible, I just say evaluate. Tell me at the end that it's divergent once you get infinity. All right, someone said, then if one integral is convergent, then the other one is divergent. What would be the conclusion? The conclusion is that it's divergent. All right. If you have 2 integrals, so if you can split this one into 2, and one of this piece is divergent, then the whole thing is divergent. All right. Let's look at our last example. The last one is a nice one. So we're just integrating 0 to 1 of ln x. What's the first thing you do? Now that you're all good mathematicians, you test your bounds, right? What is ln of 0 if I put this 0 there? Straight on, you can see that ln of 0 is undefined. So you've already seen the discontinuity, already seen the problem. All right. Obviously, ln of 1 is 0, so 1 is fine, but you know that there's a problem here with 0. Is there anyone saying something? I think I heard someone asking a question. All right, no question. So because the problem is with 0, what do? Introduce limit. And you say limit as t tends to 0 from the right, right? The integral of ln, obviously you're going to use integration by parts, is one of those that you also don't need to prove when we did by parts. If you check in your textbook, it's written in a box, meaning there's a formula that you can just state. The integral of ln is just x ln x minus x, something else you need to remember. Even if you forget, just use by parts. You end up with the same result, all right? And if you plug in upper bound minus lower bound, you end up with something like this. Now, this looks like an example we've done before because obviously we know what the limit of a constant is, it's just a constant value. We know what the limit as t tends to 0 of t is, it's just 0. But what happens here? If I plug in 0 here, I have 0 times ln of 0 from the positive side. So let me sketch this ln stuff again for the 3rd time so that you guys see what is happening. That is 1 And this is an asymptote because n equals at 1. That's my line graph. Now, when t approaches 0 from the right, remember this is 0, all right? From the right means in this direction, all right? What do you observe? You see it's heading towards minus infinity. Do you see that? Because it's heading towards minus infinity, this substitution here, if I have to plug it in here, I'll end up with something like this, or end up with 0 times minus infinity. Ha, that rings a bell, right? This is L'Hopital indeterminate form. Once you see 0 times plus or minus infinity, you know that you can rewrite it and apply L'Hopital. In this case, it's easier to keep ln at the top and take t to the bottom. So we take t to the bottom, write it as 1 over t, all right? Then make sure that this expression can simplify to what you started with when rewriting. And do you guys remember why we're rewriting in this form? Because we want to get it to either 0 over 0 or plus or minus infinity divided by plus or minus infinity. Once you can get it to any of this form, then you're good to go, all right? In this case, let's see, if I put 0 there, I get infinity at the bottom, 1 over 0 is infinity. You see, I end up with infinity over infinity, which is good. It means I can apply L'Hopital rule. L'Hopital rule says that I differentiate the top and the bottom separately. Derivative of ln is 1 over t. Derivative of 1 over t is just minus 1 over t squared. If you simplify this whole maths here, you just end up with just minus t. All right, it simplifies to minus t. Is it that? And the limit as t tends to 0 of minus t is 0. You see, it works. It's convergent. All right. Therefore, this integral becomes, let's go step by step, where you use minus 1, it remains minus 1 because limit does not affect the constant. For the limit as t tends to 0 of t times ln of t, you've shown it here, 0. And finally, this last one, the limit as t tends to 0 of that constant t is 0. And your result is just minus 1. There you go. Good to go. Any question from your side? Guys, don't assume that you know this stuff. Practice. Do this homework question. Do the third question. Very, very important. Make sure you're able to do the third question.